Hi, my name is Remy Cotterer. I'm a physics major at Vassar College, and I just completed my sophomore year. While physics definitely can be intimidating, it is also an incredibly important subject to learn, as it is the basis for most modern technology, and it is fundamental to learning how the universe behaves. The Contemporary Physics Education Project, CPEP, is a nonprofit organization that aims to provide students and professors in need of teaching aids with visually appealing resources that present an understanding in a multitude of physics subfields. The nonprofit has 5 excellent detail-oriented posters and other resources listed under each specific poster that help people further learn about a desired topic. As a student primarily interested in energy physics, the chart titled Fusion, Physics of a Fundamental Energy Source had a great appeal to me. I had some background knowledge on fusion reactors, but didn't completely understand the processes involved and the conditions needed for creating fusion energy. I expanded my knowledge greatly by using this chart and by looking at the interactive plasma physics experience, which was a resource that CPEP recommended. I suggest that anyone interested take a look at this chart, but I will also discuss my new understanding of fusion and plasma physics. Currently, nuclear energy originates from a process called fission, which is the splitting of atoms, and the excitation causes a very large amount of energy to be released. Unfortunately, the radioactive waste products produced from fission reactions are harmful and toxic to the environment and are not sustainable long term. That's why fusion's important. A fusion reaction occurs when 2 low-mass nuclei combine or fuse to form a new nucleus. The process releases energy because the resulting mass of the single new nucleus is less than the mass of the individual nuclei, and thus, using Einstein's E equals mc squared, the leftover mass is then converted into kinetic energy. Fusion is the same process that is constantly occurring in the plasma core of our sun and in other stars. To create proper fusion conditions on Earth, though, is very difficult and requires a mechanism to generate and sustain plasma. Scientists have been trying to reproduce fusion reactions on Earth in a controlled manner in the hopes of providing a long-term, sustainable, environmentally friendly, cost-efficient, and safe energy source. The 2 fundamental fusion processes are that between deuterium and tritium and the proton-proton train reaction. Deuterium and tritium are 2 hydrogen-containing isotopes, and when the 2 fuse together, they form a helium atom, and high-energy neutrons are released. The proton-proton chain reaction is the process that powers the sun and is a chain of thermonuclear reactions where protons combine to form a helium nucleus, and the mass lost in the process is released as kinetic energy. For fusion to occur, it requires optimal confinement conditions of plasma at a temperature in the region of 200 million degrees, and the fuel density must also be massive. Plasma, often called the 4th state of matter alongside solid, liquid, and gas, is composed of free-moving ions and electrons and has the ability to conduct electricity. At the temperatures required for fusion energy, all matter is in the form of plasma, and researchers have tried multiple mechanisms to confine and heat it. There are 3 methods for plasma confinement: gravitational confinement, magnetic confinement, and inertial confinement. Stars, they use gravitational confinement. Their gravitational field creates high pressure, which confines the plasma. However, this method isn't reproducible on Earth. Magnetic confinement uses a large magnetic field to confine the movement of plasma, and the field causes the heat of the nuclei to dissipate and thus slows down the plasma's movement, allowing it to be used as a fuel source. While magnetic confinement aims to create a continuous form of plasma where fusion can occur, the alternative, inertial confinement, works very differently. Rather than creating a stable fuel source, inertial confinement tries to compress and heat fuel rapidly to generate energy from a series of fusion reactions that produce discrete amounts of energy each time. Currently, fusion reactions are limited by the number of facilities available worldwide and the complexity of confinement techniques. While there is still further large-scale research and development that needs to be done, many innovations relating to plasma confinement and fusion technology are already benefiting our everyday lives. Nuclear fusion has the potential of being the energy of the future, and it's fascinating to learn about a field of physics with such huge implications.